Thank you.
Yeah.
Okay, thank you, Prof. May, for the introduction. And the title of my talk today is Conditional and Collaborative Neural Heuristic for Solving Multi-Objective Weak Routing Problems. And in this talk, I will share two of my recent works. First, I will give a brief introduction and some background, and then I will describe a conditional neural heuristic method, which is a transformer-based deep model to solve multi-objective weak routing problems. Then I will describe the collaborative deep reinforcement learning method, which is proposed in another work. And finally, I will give the conclusion. So here are some information about myself. So except traditional weak routing problems, I'm also researching on developing some deep models to solve complex combinatorial optimization problems, such as airport ground handling problem, train metro scaling, and road network design problems. I'm also trying to use some deep learning techniques to solve integer programming problem and to enhance the solving performance of some exact solvers such as Groby, Cplex, and SIP. And today I will, in this talk, I integrate the two of my works. The first one is published in TNLS journal, and another one is published in AMAS. So here is a brief introduction. So why do we use deep learning for solving weak routing problems? Sorry. First of all, weak routing problems are a class of NP-hard problems, combinatorial optimization problems. It means it is very hard to achieve the optimal solution in a polynomial time limit. And because of this NP hardness, the researchers in operations research and computer science community often use heuristic or meta-heuristic methods to solve weak routing problems. Because if you can also apply some exact solvers, but these solvers would get the optimal solution with maybe hours and days to get very elegant solutions. So the heuristic methods are often used to solve these complex problems. And but for the heuristic or meta-heuristic methods, you often need some domain expertise or some like trial and errors to tune your heuristics, maybe to the hyperparameters, or you need to choose which operators to use in your algorithm to make your algorithm achieve very good performance. For example, if you use a genetic algorithm, you need to determine which cross operators you use and what is the crossover probabilities in the operator. So you have a lot of these configurations to choose and many hyperparameters to tune. So it will cost you a lot of effort and time. So deep learning can be used to mitigate or relieve this effort. For example, we can collect a lot of data, a lot of instances, and then we can just build a neural network to learn the policies, to learn the heuristic rules to solve the problem. So based on a lot of data, the neural network can learn a promising policy and in a acceptable time, and it would also save you a lot of effort. But now a lot of research is put on the deep learning methods for solving single objective wave routing problems. There are still only a few works towards solving multi-objective wave routing problems. So in this talk, I will describe two of our works which are developed to solve the multi-objective wave routing problems. So so this is background. I want to give you some background about single objective wave routing problem. Here are two typical wave routing problems. One is TSP and one is CVRP. And in TSP, you need to find the route to traverse each node once, and the objective function is to minimize the length of the route. And in the CVRP, there is a constraint of capacity. So your vehicle has a capacity. You need to serve the customers with demands. So the capacity cannot be over the total demand of the customers in a route. So every time the capacity is consumed, so you need to let the vehicle return back to the depot and then start again to serve another set of customers. And to solve these single objective wave routing problems, now the main deep learning method is using the deep reinforcement learning algorithm to learn the policy to construct the route. It means we want to learn a policy to select the node one by one. It means serve the customer one by one, and finally return back to the depot. And so if we consider this node selection as a sequential decision-making problem, so we can naturally or easily model it as a Markov decision process. So imagine we have an agent which is represented as a neural network pass data, and given the current state, which means maybe the current node and maybe the current visited node, this is the state. Given this state, the neural network or the agent can pick the next node according to the current state. And after selecting the action, we can get the next state and a feedback or a reward. And yeah, we can let the agent to interact with the environment with this. The environment means a problem instance. We can just let the agent to interact with the environment and collect the trajectory of a state and action, and then we can just put this trajectory into the reinforcement learning algorithm. So here I gave two typical reinforcement learning algorithm. One is called reinforce algorithm, and another one is actor critic. And so I would not give too much details, but for reinforce, it is Monte Carlo sampling methods. It means you just collect all the trajectories, and after that you compute the total future reward at each step, and then you use this total future reward at each step to update your action at this step. So this is the logic of reinforce. And for the actor critic, because the main drawback of reinforce is that you need to collect the whole trajectory, and then you can compute the reward. But it may not be efficient because you need to just sample all the trajectory. So in the actor critic, it uses another neural network, which is called the value network. This value network is used to estimate the total future reward. So the V means here the V means value neural network, and we can use this estimated future total reward to update the policy network, update the neural network used by agent Pi. And now the current literature often use the first one, the reinforced algorithm, because we can easily sample the whole trajectory and then compute the total reward, which is the total length of the route. So it is a very natural and easy mapping relationship between the reward and objective function. So now the most literature use this reinforced algorithm. And yeah, here I give the update formula, which is often used in the literature. It is just a variant of this reinforced algorithm. And for the policy network or the neural network used by agent, we often use encoder decoder based transformer model. So we input the information of instance, for example, the coordinates of customers. We input this information into encoder, and then we use some self-attention layer and skip connection and a normalization layer to advance this node information to get the node embeddings or node vectors, which represent the high level information of these nodes. And after that, we use this node embedding to do the cross attention. It means we use linear transformation to process the current dynamic feature. For example, how much capacity is remaining in the vehicle in the current step. So this is the dynamic feature. We will linearly project this information into a context embedding, and this context embedding is used to do cross attention with the node embedding, and then we can get we can just use softmax to get the probabilities over these nodes. And with these probabilities, we can just sample which node is going to visit in the next step. So the background is over. So in our first work, we developed a transformer-based neural network on top of this structure. And so if we see the difference of multi-objective vehicle routing problem and the single objective vehicle routing problem, the main difference is the preference of different objectives. So in multi-objective vehicle routing problems, we have different objective functions. For example, in CVRP, in a single objective CVRP, we only concern the minimization of the length of the tool. But in the multi-objective vehicle routing problem, we may also focus on how to minimize the longest route in the tool. So we have different objectives. And for each objective, we will have a weight for the objective. All the weights for objectives is called preference. So the preference is you can imagine the preference is a vector, and in the vector each element is a weight for each objective. And yeah, here is a two objective CVRP problem. So in this problem, we not only search a solution to minimize the total tool length, but we also want to minimize the length of the longest route. So for this multi-objective vehicle routing problem, there is no single solution for the optimality. So it means there is no single one optimal solution. We need to search for all the Pareto solutions. So what are Pareto solutions? So here is the definition. So because we have different objectives, given a solution, we can just input the solution into the objective function, and then you get different values for these objectives. And we call the solution is Pareto optimal. It means it cannot be dominated by other solutions in the objective space. So here is an example of two objectives. So we can see here the solution A cannot be dominated by any other solutions. So you can see the solution B is better than A for objective 1, but B is worse than A for the objective 2. So there is no solution which is better than A for every objective function. So in this case, we call the solution A is Pareto optimal. And so for the multi-objective vehicle routing problem, our goal is searching all these Pareto optimal solutions. And the typical method is decomposition. So and the widely used framework is called MOVRP. It means we just transform the multi-objective vehicle routing problem into a group of single objective vehicle routing problems. And here are some different approaches to realize this transformation. So the simplest one is weighted sum approach. As I mentioned, the preference is a vector of weights. So we can just calculate the weighted sum of the objective value, and then we can get this single objective function. And we can just change the preference into different vectors, and then we can get different single objective vehicle routing problems. And also you can use Chebyshev approach and PBI approach to realize this transformation. So for different types of this decomposition approach, strictly speaking or weakly strictly speaking, so if we just solve the group of single objective vehicle routing problem and get all the optimal solution for this single objective VRP, then we can just obtain the Pareto optimal solutions for the multi-objective vehicle routing problems. Yeah, in other words, we can just solve a group of single objective vehicle routing problems, and the optimal solutions of these single objective problems are are the Pareto solutions to the multi-objective wave routing problem. And so so based on this this thought, we can just we can just give give different preferences, and then we can just try to solve each single objective wave routing problem. But you can imagine the preference is a continuous vector. You can give any value to each element in the preference. So you may have a lot of preferences. So in this case, the neural network is a very suitable method to handle this situation, because we can just use the parallel computing power of a neural network to solve this different single objective wave routing problems in parallel. So we propose this transformer-based neural network to solve the group of single objective wave routing problems. So given multi-objective wave routing problems, we first just sample a group of preferences, and for each preference, we will input the preference with the information of instance, and to fully interact the preference and the information of instance, we will use this multi-head dual attention. It means in this attention computation, we not only do the self-attention for the preference and node coordinates, but we will also do the cross-attention between the preference and node coordinates. So because the preference, we would consider the preference is a special information, which is not the instance information. So we want to highlight this preference information. So we add this cross-attention computation in the attention layer. So because we use both self-attention and cross-attention, so we call this attention layer dual attention. And we also use multi-head scheme in the self-attention, following the traditional way in the transformer. And then, except this design, we also add a size embedding, because we want our method to solve different sizes of instances. We don't want our neural network is trained for one single size and then can only be used to solve this single size. We want it to be used to solve a group of problems with different sizes. So we add this problem size as additional information, and use position encoding to get the embedding of this size, and then we use the linear projection to process the problem size into another embedding, and this embedding is added to the node embeddings from the encoder. So compared to the if we compare this structure and our structure, you can see we just adjust we will adjust the computation in the self-attention layer, and also we add the size embedding into the node embedding from the encoder. But we see these two simple change can bring a significant improvement of the solving performance. And here the reward for each single objective VRP. As I mentioned, you can just use the weighted sum or Chebyshev decomposition to get the objective function for each single objective VRP, and this objective function can be used for the reward to update the neural network. And for this gradient update formula, which so it seems complicated, but here the B is the batch of instance, and for each instance we do some argumentation to collect the extended set of instances, and we collect these gradients and do the back propagation to update the neural network. And here, because we input the size embedding, so in the training we just train our neural network with different sized problems, and we train the problems of size 20, 40, 60, 80, and 100. And yeah, this value means how many nodes exist in one instance. And for the stochastic preference, yeah, this is a small design which is different from the literature. So in the literature, they just sample the preference with the values. So in the literature, the elements in the preference must be added as one. But in our paper, we just relieve this constraint. We sample the element in the preference from 0 to 1, and we just input this more random preference in the neural network. But finally, if we compute the reward, we will still normalize these values into the values with sum 1. But as the input to the neural network, we make this preference more random and giving up this sum 1 constraint. It means it seems like we are doing some data augmentation for the preference, and we also find this simple change brings a lot of improvement. And here is the result, and we test our training neural network to solve the 2 objective TSP, 2 objective CVRP, and 3 objective TSP. And we also test the neural network on the sizes which is used in the training, and we also generalize our neural network to the sizes which are not used in the training. And yeah, in the left part, the testing performance shows that our method called CNH generally achieves better results than other neural heuristics and some traditional heuristics. And for the generalization performance, our method achieves the best performance for all the instance groups. And we also test our neural network on some benchmark data. And we find our Pareto front is better, which means it is more towards to the left lower corner of this objective space. And we also did some average study, because our neural network can be trained with different problem sizes. We find we can just train one unified neural network with very short time limit, and for the other neural heuristics, they need to train each model for each problem size, which cost much more time. And we also test the main design of our problem, for example, the cross attention and the embedding of problem size. And we found that they are performing very well. And in the second work, our goal is further increasing the generalization performance of our neural network. So we proposed the collaborative deep reinforcement learning. The motivation is displayed in the slide. So we found that the deep learning based methods in the literature are trying to imitate the traditional MOVRP methods. Yeah, it means we just like give a group of preferences and get the subproblems, get the single objective vehicle routing problems for each preference. And then we just learn how to solve this single objective vehicle routing problems much better, and improve our neural network according to this, according to the performance on each single objective vehicle routing problems. So this is the main logic of the methods in the literature. But compare these methods with the traditional MOVRP method, we find that the interaction between the single objective vehicle routing problem is missing in the current neural heuristics. For example, in the traditional MOVRP methods, they often used some local search or genetic operator to evolve the solutions from different single objective vehicle routing problems. And if a better solution is found for a single objective VRP, then it will replace the previous solution. But the traditional MOVRP also apply the solution of each single objective vehicle routing problem to other single objective vehicle routing problem in a neighborhood. The logic is that if the preference vectors are similar, so the subproblems, the single objective vehicle routing problem, may share some similar problem structure. So it means if a solution for a single objective vehicle routing problem is very good, so maybe we can just think that it would be also very good for another single objective vehicle routing problem in the neighborhood. And the neighborhood means a group of single objective vehicle routing problems with similar preference vectors. So we found this interaction between the star problems is missing in the neural heuristics. So here we propose to based on our previous method, we just apply the imitation learning in addition to the reinforcement learning. It means at each step at each update step, we will just check the current best solution of each single objective vehicle routing problem, and we see how it performs for the single objective vehicle routing problems in the neighborhood. So if this solution is better for any other single objective VRP, we will just replace the previous solution with this better solution. And then we use this better solution as a label to train our neural network. So it is called imitation learning, but it's, basically it is just a supervised learning. We just find the best solution in a neighborhood for each subproblem, and then we update the neural network with this best solution for the single objective problems. And so finally, we use this joint optimization with both reinforcement learning loss and imitation learning loss. And here is the result of this joint optimization of reinforcement learning and imitation learning. We found that this imitation learning brings a lot of inference time than other methods, but it indeed brings a lot of improvement in terms of the performance, the hypervolume. And here we also test our collaborative DIR on some benchmark data set, and we also found it achieves the best hypervolume compared to the previous methods. So to conclude, so in this talk, I introduce two of my works. The first one, in the first one, we propose a dual attention based transformer deep model to relate the preference and instance information, and to get better representation learning of the instance information and the preference. And then we add the size-aware embedding module in the decoder, and to let the neural network be aware of the problem size. And then we can train one unified neural network to solve a group of problem sizes. And in the second work, we propose the collaborative DIR method to interact the subproblem solving to make it more similar to the traditional MOVRP, but it is a neural version of the traditional MOVRP. Yeah, that's all. Thank you.